I would love a situation where I could talk less and you would do more, but a lot of people were like, you didn't even teach us this! If I didn't like yell it at you at some point, you're like, remember this, blah, blah, blah. Like, then you take a test and you're like, did he tell us this?
Please excuse the interruption.
IED drill?
At this time, please release 10th graders with the last name A through G.
IED drill?
Okay, I have a question for you. My question is very simple. The rockets that we build and we launch are not normally assembled where they're launched. For instance, the rockets that Russia and France and, well, the European Space Agency, the rockets the European Space Agency launch are assembled in Europe, put on a boat, and sent to French Guiana. There's a map of French Guiana over there. It's in the northeast of South America, all the way across the ocean. And the rockets that we build are assembled in California and Pennsylvania and Texas, and they're launched from Florida. Why do we spend so much time putting a rocket on a train or a boat and sending it to a launch pad far, far away? Why do we do that?
Those are kind of like close in area.
You realize that this is South America.
It's like
France is up here.
Well, no, I'm talking about like the launch.
Russia's up here.
I'm talking about like the launch sites, Florida and that Brazil area. They're kind of close to like the middle, or you know how like the Earth is the lower hemisphere is kind of like the middle. Is that like close to like the center of mass of the Earth or something?
You're getting there, yeah. So Florida is as close to the equator as we can get, safely, securely. It'd be great if we could launch out of Mexico or Cuba, but we're not there yet. And French Guiana is almost entirely on the equator. So why do we do that?
I'm guessing where it's launched deals with the fuel that they use, because they run off like hydrogen, oxygen fuel. If you burn straight oxygen, it goes.
Okay. So yeah, it does have something to do with fuel. Scott.
Wouldn't just if it's near the closer to the equator it is, the closer it is just to being like getting to outer space, so like it's closer to the sun and stuff like that.
Okay, well, you're getting there. Just realize that the Earth is a globe. So the atmosphere is pretty much uniform, pretty close to uniform everywhere. It's a little bit thicker near the equator, but you're all getting there. Yeah.
Isn't like the closer to the center of the mass or something, it helps with the orbit?
Mm-hmm. There is definitely a reason, and it's considerable enough that the Russians put their rockets on a boat and send them 6,000 miles to South America. So what else might it be? If you were standing on the rotational pole, the North Pole, where Santa Claus is, and you were to illustrate your motion with respect to the Earth, what would that motion look like? You'd be like this, right? Okay. And then if you took one step over, what would that motion look like? You're kind of walking in a tiny circle.
Yeah.
And if you were further out, you'd walk in a bigger circle, right? And the further you are from the pole and the closer you are to the equator, the bigger that circle is going to be, right? Well, here's the crazy thing. By putting a rocket on a boat, sending it across the Atlantic Ocean, and launching it from the equator, you actually give that rocket rotational velocity. The rotational velocity of you, while you're at the North Pole doing this, is 0. The rotational velocity at the pole is a lot faster. So when you walk from the North Pole to the equator, you're not just going south, you're also going east. You're basically, as you aim your compass directly south, you think you're going south, but according to the world, the solar system, not only are you going south, you're also going east. Or west, because it rotates west. You're going west. Okay? Does that make sense? So objects at the equator have maximum rotational velocity. So we use that because when we launch rockets near the equator, they already have a lot of the velocity we want them to have to get into space. If we launched a rocket at the North Pole, it would have to go up, but then also over. Realize that objects that orbit the Earth orbit around the Earth's axis with the equator. So if we launch at the North Pole, we'd have to go up out of the atmosphere and then turn 90 degrees and go over. If we launch at the pole, we can basically just go up and we already have a whole bunch of rotational velocity. Make sense? So that's what we're talking about today. We're talking about how things spin, how things balance, and how things rotate and what causes them to rotate. So we're talking about everything moving in a circle. Torque, center of mass, circular motion, and universal gravitation. This is a great diagram we're going to use a lot. You've actually seen this diagram when you learned about vectors. Objects moving in a circle have a velocity vector and an acceleration vector. The velocity vector is always tangential to the circle. What does that mean, tangential? Tangent to the circle? What does that mean?
Like pointing out from it in a straight line.
Yeah, pointing out from a straight line, that works. So my fork is tangent to the bottle.
Oh,
Okay. So my fork is tangent to the bottle. Tangent to the bottle. Okay. My fork is tangent to the graduated cylinder. Okay. Pointing out from it a straight line. So the velocity vector of an object moving in a circle is tangent to that circle. The acceleration vector is perpendicular to the velocity vector and is what we call centripetal. Center seeking, centripetal. Like the petals of a flower are all connected to the center. They all point towards the center. So centripetal is center seeking. The acceleration vector is centripetal. It's pointing towards the center. Make sense? I have many times lobbied the powers that be to put up tetherball poles, like portable ones. You know, you pour the cement into the tire and put the pole in there, out in the quad. But they always look at me like, is this elementary school?
yes.
Well, I think it would be, kids could, you'd like that, right? Play tetherball during lunch? That's better than you're like, I'm playing Clash of Clans. But you could be playing tetherball. Well, the great thing about tetherball is when you hit something, you tend to hit it with a velocity or a force, with momentum that is tangent to its movement. You tend to hit it like bam, and it goes around. And what causes it to go around? The rope, yeah. If you cut the rope, then where does the ball go?
Forward.
In a straight line, right? So that rope produces a centripetal acceleration that is directed towards the pole. Okay? Give me a thumbs up if that concept makes sense to you. Cool. So linear velocity is how fast an object moves through space in meters per second. Circular velocity is how objects move through space in a circle in meters per second. And then angular or rotational velocity is how fast an object spins, moves over an axis or around an axis, and that's going to be in radians per second. Now here's the good news. Unless you go on and take more advanced physics, you don't have to worry about radians per second in this class. Okay? In this class, we focus entirely on meters per second. We don't do radians. Okay? We don't use Greek alphas and betas and omegas and all these for velocity. We're just going to focus on meters per second. Now, the reason that's important is if you want to know how fast you're going in a circle, the word you're looking for is circumference. 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 And that is going to be 2 pi r. You know circumference, right? 2 pi r? So the circumference is diameter times pi. Pi is the ratio of a circle's circumference to its diameter. Okay. So if you want to know how fast something's going around a circle, you're still looking at a velocity. Oh, I've got to break rules. Velocity is still going to be distance divided by time, but now we have new velocities. We're going to say velocity circular, and the distance is going to be 2 pi r, and the time, we're going to use a new variable for time. We're going to basically use a variable that means all the way around. One around and around. Just one around. And that is period, which is a capital T.
What?
Period. Okay? So if we want to know our velocity, we can take the circumference of a circle and divide by the time it takes to move through that circumference of a circle, which is period. 2 pi r, circumference, capital T, period. I'm sorry?
What happened to your bird?
Someone broke it.
Yeah, but I have another one. I'll get it out in a little bit. Yeah, I got another one. I should 3D print these. There's actually cool. You guys should 3D print these and put nuts in there. So 3D print some birds. But yeah, I got another one in the closet. I don't know where my old one is.
Don't 3D print the bird, 3D print the same like concept but a different thing.
Or it might be in the fidget bin. I bet it's in the fidget bin. I would lose that bet. Okay, the old bird is gone. I'll get the new bird. Okay, so moving on. All right, so when you apply a force on an object, that force produces a what? When you apply a force on a mass, that force produces a what? Acceleration. So forces, troll face dot rude.
I think that's Russian too.
Yeah, of course it's Russian. Yeah, of course it's Russian. So when you apply a force on a mass, that force produces an acceleration. Yeah? Well, if you apply a force in a rotational kind of way, it produces not a force, but a torque. Torque is given the letter script T, which is tau, and torque is used when you want to apply motion in a circular kind of motion. When you want to apply a force in a circular kind of motion, you use torque, which is tau. And the formula for torque, well, what two things, if I'm going to, I don't have my wrench, here, let me get my wrench. Of course I have my wrench, the wrench is right here. Here's my wrench. Okay. So if I want to move the bolt, let's see, imagine I want to move the bolt. I want to get the bolt going. You can't see here, but I'm getting the bolt going. Here we go. What must I apply on the wrench? A force. I got to apply a force, right? Because if I don't apply a force, then nothing's going to happen, right? And what if I apply the force this direction, pushing down? Is it going to move the bolt? No. No, this thing's going to stay right there. But so I'm going to apply a force like this, perpendicular to the tool, right? The tool is called the lever arm. The length of the tool is called the lever arm. So I apply force like this. What if I applied force way down here, pushed right here? Am I going to get much done?
Don't have a whole lot of leverage.
Not a lot, right? And I need more leverage, exactly. So I'm going to push up here and I'm going to get more leverage. And in fact, there's these things called cheater bars where you can put a steel bar on the end of your wrench and then you can use that as long as you don't break the wrench itself. But you can put a cheater bar, which basically allows you to move it from way up here and dramatically increase the lever arm. So if you were to come up with a formula for torque, then tau would equal what times what? What do you think? Force times the lever arm distance, exactly, the lever arm. So that's what we get. So tau is force times distance. Okay? The force applied multiplied by the lever arm gives you the torque. Now we're almost done. This is not the entire formula, but we're almost done. There is one more thing we need to add. One more element to the equation to make it accurate. And that is, if I was to pull or push, if I was to push on this straight down, am I going to get any rotation? No. If I was to move perpendicular, I'm going to get maximum rotation. So is there a trigonometric function where 90 degrees is maximum and 0 degrees is minimum? What trig function is maximum at 90 degrees and minimum at 0 degrees? Sine, exactly. So we got to put a sign at the end too. So the formula really should be tau equals FD sine theta. Okay? So yeah, the formula is FD for tau, force times distance, but we really should add that sine theta in there because sometimes we're not able to apply a force perpendicular to our lever arm. Sometimes we just can't. That's just not the way it works. As you might imagine, I spend a lot of time on Imgur. It's like, oh, I can use that in physics. Copy paste. So does this make sense? All right. So let's do another. Idea. So you know that game that losers, juveniles play, where they like try to hold a door. It's usually a boy trying to hold the door closed for a girl. Well, let's pretend that Eli's playing this game, and Eli's inside, and he's trying to push on this side of the door right here, like like 10, 20 centimeters from the angle right here. And then Alyssa's like, no, I'm smart. I'm going to push the door way over here, far from the axis. Who's going to open the door? Alyssa, because she's got a much longer lever arm. Okay? And so again, when you're playing that game, make sure you're pushing as far from the hinge as possible. You want to increase your lever arm as much as possible. Okay, give me a thumbs up if this makes sense to you.
Sorry, I was just
Okay.
following the
Give me a thumbs up if we're good to go. Wave your hand around if you have questions. Moving on. All right, so center of mass. The center of mass is the point at which all torques balance. Okay. My bird, my bird. I'll get my bird in the cover in a second. So the center of mass is the point on an object where all the torques balance. And a classic example of an object that has a center of mass right at its axis is a...
At this time, please release 10th graders with the last name H through P. Please report to the library for screening.
Is a meter stick or a yardstick. So this is not a meter stick. This is a yardstick, which is why I painted it black and I use it for whacking things or holding things. There's a magnet on the end. If let's just pretend, just to make the math easy, let's just pretend this is a meter stick, and it's 100 centimeters long. It's not. It's my GoPro gimbal. I don't need this anymore this year. I haven't used it in a while, but it's my GoPro gimbal, so I can stick it to the ceiling and then take videos and stuff. But let's say this is a meter stick. It's not. It's a yardstick. Let's say it is. Where is it going to balance?
It would balance.
1.5 meters? No, half a meter.
At 50 centimeters, right? Because at 50 centimeters, the chunk on this side has the same torque as the chunk on this side. What's providing the force to produce the torque? Gravity. Gravity. And does that make sense? So gravity on this side, gravity on this side?
Yeah.
All right. If that makes sense to you, this is important. Pay attention. If that makes sense to you, I'm going to just hold this right here. Where on this object is the gravity acting?
The ends in the middle.
Only the ends?
The whole thing.
Here's the thing. When you're doing math, you look at the center of mass of the piece. So if the piece is from 50 to 100, then the gravity acts at the middle of that piece at 75 centimeters. And if the piece is 0 to 50, then the gravity acts at the middle of that piece at 25 centimeters. Does that make sense? Because that is the center of mass of the piece. The center of mass of the entire ruler is at 50 centimeters. And the center of mass of the first piece is at 25, and the center of mass of the second piece is at 75. Does that idea make sense? Okay, it makes sense to everyone but Seth. This is like I understand at some point. It's like, okay, so let's go ahead and just my gimbal away here. So again, center of mass is where all the torques cancel out. We have a special name for this. We call it equilibrium. We used the word equilibrium when we were talking about all the forces canceling out. Now we're talking about equilibrium where all the torques cancel out. And this is torque left, torque right. Oh my goodness. I have way too many projects going on. Orbitals. These are for one of your challenge slides at the end of the unit. Kaminos. Sweets.
So sweet.
One of the teachers I used to teach with 9 years ago, she still sends me stuff.
Sugar.
Yeah, she'll send me sugar just because she's awesome. Yeah, she's totally awesome. And she could retire. I think she has more years in the district than Bill. Yeah, she's like hardcore.
Oh.
Yeah, he's got 35 years in the district. So he could retire at any time with full pension. Okay, anyway, so boom. Where does a bowling ball balance?
Bowling pin.
Right there on the hump. You might have actually played, if you were playing bowling, you ever seen the bins hit and then spin? They're designed to spin and act like a saw blade taking out the other pins. So they are actually designed to spin at their hump. Yeah. Doesn't balance quite exactly right, but at the hump right there. If you were to cut it in half at that point and weigh the two halves, I had a student who said, like, challenge accepted, and she got 2 bowling balls and gave it to her father who had a bandsaw and cut it in half. Or 2 bowling pins. So if you were to cut the bowling pin right where it balances, she cut it a little bit on this side, but that's okay. If you were to cut it right where it balances, how does the fat part compare to the skinny part in their mass? Which weighs more, the fat part or the skinny part?
The fat part, but the reason the part is
right down
the distance is T left equals T right.
So the masses are the same because T left equals T right? So why don't you chat with your neighbor, take a minute and say, based on what I know about torque now, that FD equals FD, that the fat part is going to weigh more or less than the skinny part. Question or answer?
Well, I'm just going to, I guess, answer.
Okay, then chat with your neighbor. So take a minute and chat with your neighbor and decide which of these 2 chunks weighs
The
more.
fat part weighs more, but the not fat part is longer, so like that evens it out, you know what I'm saying?
So it's equal weight.
So like it'll end up being the same torque.
balance
So
in
basically
the middle,
it's the
and
same-
you cut it
The
at the
exact
middle.
same torque, but you know how like force times
I heard you
distance.
say
I think they're balanced.
And so if that one weighs more, it has a higher torque, you know, you multiply the kilogram by 10 torque, and then it has a lower distance. Well, the other one has lower weight, but a higher speed.
All right. So it seems like you guys have spent a little bit of time. If you believe the fat part is heavier than the skinny part, raise your hand. About a third of you? Okay. If you believe the skinny part is heavier than the fat part, raise your hand. If you believe they're exactly the same, raise your hand.
They should be.
About the balance. No, they're not. The fat part is heavier. Oh, Mom, get the camera.
I'm better now.
Okay, why is the fat part heavier? Because this distance, look at this, the axis is right there. This one has a small d, this one has a big D.
I got it.
The thing about having a small d is you have to have a big force.